So today we will be doing the magnetic field problem, number 3 from the homework, and the problem is it says point P is at a distance r away from a straight wire of length L, carrying a current I as shown in the figure. So we're going to do part A first. Part A is what is the magnetic field vector at point P. And the first thing that you should be thinking when doing these type of problems, so for me, is figuring out which formula to use. And in this case, since we're doing magnetic field problem, then that means that we have two choices. We have Ampere's law and BS law. And it should be pretty obvious that we have to use BS law because it's a finite length. It says that this straight wire here from part A is length L. So we will be using BS law for part A. And BS law is going to be dB is equal to mu naught over 4 pi times IDL cross of R over R squared. And in this case, BS law is pretty simple to understand. It gives you it tells you a tiny amount of magnetic field coming from a little bit of DL. DL being a very small length of a conductor carrying current, and in our case, it's this straight wire of length L. And it's important to understand that this is a unit vector, not just a R vector. So this unit vector specifies the direction of the vector distance R from the current to this field point right here. So I'm just going to redraw this diagram. So we call this distance R, and we can look at this little tiny current coming at this point right here. So if I was to label this axis X, then that just means that we're going to be sampling a little tiny dx, right? And it won't be dl anymore because we labeled this axis X. And that means that this distance to this distance is just going to be R. And then we can call this angle theta. Sorry, I didn't mean to draw it. Let me just fix this up a little bit. Okay. So this is the distance from the wire from this point, and this is little r is the distance from the current. And then we can call this side x. So if I was to rewrite the equation to how we label this diagram, it will be as followed. dB, everything will be the same except it will be I dx cross of R theta over R squared. And now we just simplify this problem and plug in what we know. So cross product, this part specifically, right here, we're crossing two things, and it's important to know that anytime you're doing cross product, A cross B is just equal to AB sine theta. Theta being the angle between the two vectors. So in this case, we have a dx and then r. So we're just gonna get this equation, mu naught over 4 pi I dx sine theta over r squared. And in this case, because we know what theta is, it's very simple to simplify. If I was to write, do you guys remember the good old trick SOHCAHTOA? We can actually replace sine theta with opposite over adjacent. And in this case, our opposite is going to be capital R, and then our hypotenuse is going to be little r. That means we can replace sine of R over R, and it can be written as this, mu naught over 4 pi times I dx r over r squared times r. And this was our sine. So, another important thing to determine is also which direction is the magnetic field going, and this is a really important question that you need to answer. And of course, we have to use the right-hand rule, right? Where our thumb is going to be our current, and then the magnetic field is going around it. So in this case, sorry, it's very awkward to do, but in this case, if I was to, for example, find out the direction of the magnetic field at this point right here, it would be my current's going this way, my hand going into the paper, so that means the magnetic field is going into the paper. So again, thumb goes in the direction of the current, and then you go around. And if we're looking at this point specifically right here, we're hitting the point, that means that it's going into the paper. So that means that this magnetic field is also going in, which is just this symbol right here. So moving on, let me just rewrite what we had on our last piece of paper. So we know that dB is equal to mu naught over 4 pi times I dx r over r squared r, and we know that this is going into the paper. So I think it's also kind of important to understand what this equation is telling us. So all this is really telling us is how much magnetic field is coming from this point right over here that we chose, this little dx term. This little dx term is giving a magnetic field that is dB, a very tiny amount of magnetic force. And what we have to do is integrate, because dB is just a very small magnetic force coming from a small dx, or a very small length of wire. So that means we have to integrate to add up all the magnetic forces coming from this wire right here. So if I was to integrate both, if I was to simplify this and integrate, it would look like this. dB is equal to a integral mu naught over 4 pi times I r dx over r cubed. So what's our limits of integration for this case? It's pretty obvious. So it says that this is a length L, meaning that I can call this 0 to L. So the limits of integration will be from 0 to L. So we're going to add up all the little small dx's and all the magnetic fields coming from that small dx. So in this case, what our constants will be I and R, and mu naught over 4 pi, because current is going to be constant, and this R term will never change. So we'll just be left with integral dB is equal to mu naught I R over 4 pi. Limits of integration, like I said before, 0 to L, and all we're left with inside is just going to be dx over r cubed. In this case, it's very you can check to see if you're using U sub or trig sub. So because the numerator has a power of 0, or even if the numerator has a power that's even, we can automatically know that it's going to be trig sub and not U sub. So we have to do a trig sub here. So how do you do trig sub? What was covered in class is the first step you have to do is how to trig sub. So the first thing you should do is draw the triangle that we had before, which is just going to be this triangle right here that we drew. So I'm just going to copy this triangle over to a new piece of paper. And, oops, sorry, it's not lined up. So we have this triangle. Cosine data, x, r, and r. This is just the exact same triangle that we had on our first piece of paper right here. And after you draw the triangle, you have to relate the variable with a constant. So in this case, our variable is x because our current can be anywhere, right? It can be here, 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 meaning our x can either get much larger or much smaller, depending on where we choose the I. So x is going to be always changing, while our r term will never change because no matter what, this point will always be r distance away. And then r is just going to be a radical term, our hypotenuse. So, like I said, x is going to be a variable, and r is our constant. So this is going to call this my constant variable, and this is our radical slash hypotenuse. So that means if I want to relate my variable with my constant, I need to relate r and x. In this case, r is just going to be my opposite term, while x is just our adjacent term, and that means you have to use tangent. So tangent theta is equal to r over x. And the way I like thinking about this is you want to figure out what dx is. So we're trying to find, we need to bring x over. So we're left with x tan theta is equal to r, and then divide tangent over. So we get x is just equal to r cotangent of theta, because 1 over tangent theta, if you guys don't remember, it's just going to be cotangent theta. So now we can divide both sides. So if I was to divide both sides, I will get dx is then equal to negative r cosecant squared theta d theta. And this negative came from deriving the cotangent, because the d over d theta for cotangent theta is just equal to negative cosecant squared theta d theta. So now we know what our dx term is, which we can use later when we integrate this again. So the third step for trig subbing is to relate the radical with the constant. And then we just redraw the same triangle that we've been using. Theta, x, r, and r. So in this case, like I said before, r, tiny r, is our radical, while r is our constant. That means we need to relate this term with this term. So r is just going to be our hypotenuse, and big R is just and big R is just going to be the opposite. So how do you relate this? So we have a hypotenuse and opposite, meaning that we have to use sine. So sine theta is equal to R over R. So we now we need to solve for R. So I'm going to multiply R over and then bring sine to the other side, meaning that we're just going to have R is equal to R cosecant theta. So now going back to our original integral, so I still remember it, which is just this right here. So going back to that integral, then you just rewrite it again. We have mu naught I R over 4 pi from 0 to L dx over R cubed. So because we have everything we need to replace every term in here, for example, we know what dx is. Dx is just going to be negative R cosecant squared theta d theta, while our tiny r will just be R cosecant theta. So let's replace all the terms in here. So we know that this will just be equal to R over 4 pi from 0 to L, and replace this dx with what we figured out before, which is this. So negative R cosecant squared theta d theta over tiny r, which is just R cosecant theta. So guys, let me just make sure something, if it's still recording. Okay, so now we can just simplify this integral, right? Which is, so once we simplify this, it becomes very simple. Let's see. I forgot, this is actually cubed, right? So you have a little cube term right here. So how would you simplify this? So that means we can get rid of a few stuff. So we can get rid. So actually, maybe we'll write this real quick so it's easier to see. I will put this back later, and I'm just going to look at this for now. So if I have to make this more clear, this is our actual integral, negative R cosecant squared theta d theta over R cubed cosecant cubed theta. And then I can just cancel out these cosecant terms and this R term here. So that means this goes away, and all the left is going to just be squared, and then nothing here. So let's rewrite this. We're just going to get 0 to L negative 1 over R squared times cosecant theta. And if you guys remember what I said before, was capital R is just a constant value. So that means we don't need to integrate this. So, I mean, that means we can just bring this out, because that's not important. So I can just simplify it to negative 1 over R squared 0 to L sine theta d theta. And this is just going to be a simple integration. So the reason why it's sine here, because 1 over cosecant theta is just equal to 1 over sine theta, which is just going to be sine theta. That's how we got sine theta right here. So now we just have to integrate all of this. So that means, if you guys remember, the integral of sine is just going to be negative cosine. So we're going to be R squared times negative cosine theta from 0 to L. So because negative negative gives us positive, you can just write this as 1 over r squared positive cosine theta 0 to L. But these limits don't work with a trig function, so we need to switch this back to and relate it back to this triangle. And cosine, according to SOHCAHTOA, it's just going to be adjacent over hypotenuse. And adjacent for our case is just going to be x, and hypotenuse is r. So if we can actually write this as 1 over r squared times x over r from 0 to L, which will just give us which will just give us 1 over r squared times x over square root x squared plus r squared. From 0 to L. And now we can plug in the limits of integration. And if you guys forget what you actually need to plug into, let's look back at the original integral. We're integrating with respect to dx, meaning that we just plug the limits into x. So we're left with this 1 over r squared times L over square root of L squared plus r squared. So let's not forget, we did also have this mu naught I, r, and 4 pi term. So this will be our final result for part A. B is equal to mu naught I, r over 4 pi times 1 over r squared, and L over square root of L squared plus r squared. So I'm going to pen this down. Going into the board. And this will be our answer for part A. If you guys are getting a little bit confused, I just plugged whatever we had here and brought back the terms that we pulled out, which was this mu naught IR over 4 pi, and I just brought them back together. Okay, so now to do part B. So part B is just the same problem, but it says if the wire is then extended to a semicircle and connect to another straight wire length L, shown in this figure, what would the magnetic field at point P become? And this problem looks very intimidating, but don't worry. So I think it's important to realize that this is just 3 separate problems, right? We can actually think about it in this way. We can think about it in 3 different parts. First part, second part, and third part. All this really is 2 wires from part A combined with this little circular wire right here. So we can think about this as a little circle. So that means we already know what the B field is coming from part 1 and part 3. All we need to do is find the magnetic field for this part right here, which is a circular wire. So that means we can just use BS law again. So part B, let me just draw this wire. I'm sorry for switching papers so often. And This is our point that we're interested in, and R. Same picture. And because this is finite, we still have to use BS law. And BS law again is just going to be dB is equal to mu naught over 4 pi IDL equals to R hat over R squared. And we can do the same thing. We can call the length x, so we can just change dl to dx, or we can just leave it at dl if we really want. I can just change. I'll just leave it. I just put back dx, so we're just left with this cross product, which again, a cross b is just ab sine theta, meaning that db is just equal to mu naught over 4 pi I dx sine theta over r squared. But in this case, the diagram in this case we just use big R, like that's the distance away from the conductor or slash wire. And this R is constant, so R is going to be the same because it's just the radius of a circle, right? So the real question comes, what is our dx in this case? What are we actually taking the integral of? And if you really think about it, you can really think about this just like I said it before. Just think about this as a wire, as a little circle. And this is going to be our point P. Meaning, if you wanted to take a little sample of this wire, and this will just be our length, and this is just arc length. So, if you guys remember from trig, if we have this distance r, and then we call this little angle alpha, it just means that this little arc length right here, this r d alpha. So this is going to be our dx. That means dB is equal to mu naught I just simply replace the dx with rd alpha. So what is this angle in our case then? What is this theta angle? Because in the first problem, it's very simple because we knew what alpha theta was. It was just going to be this angle. But in this case, I believe it's not as obvious. And you can think about it as, so our dx term, or dl term, is this vector right here. This is going to be our dx term. And this is our r term. So what is this angle right here? And I can draw a bigger picture for you guys. I should just draw half of that circle. And then we call this the dl vector. And then we call this the r vector. And this is the p right here. It's simply just going to be 9 degrees, right? 9 degrees. No matter where it is, it will just always be 90. So in this case, our theta is just going to be 90. So we're just going to have and sine 90, where sine 90 is just going to be 1. That means if you know sine 90 is equal to 1, we can just take that out. We can just put 1 in there. And we know that is just 1. So, like what I did before, integrate both sides, right? Because we want to figure out how much magnetic field that this circle wire is giving us. And we're just sampling it by the arc length. So I'm going to just integrate both sides. Integral of dB is equal to mu naught so this is a constant, this is a constant, and then it's going to integrate I R d alpha over r squared. In this case, what's the limits of integration? We can look at this actually, because this is really what this part of the wire is. Part 2 is simply just a wire like this. And if you think about this as a circle, this will just be from 0 to pi. And that is going to be our limits of integration. So the integral of dB is just going to be b. You know, b is just equal to mu naught over 4 pi 0 pi I over r, because this r cancels with this r, d alpha. And then I and r are just our constants. So that means we're just left with b is equal to mu naught over 4 pi I over r 0 to pi d alpha. And this integral will obviously just be pi, because we're going to be left with, I write it down. Alpha from 0 to pi, and this would then just be equal to mu naught over 4 pi I over r as pi. And it's still going to be into the board, right? Going back to the diagram. If you think, if I'm looking at this current that's going at this angle right here, my thumb, it's still going to be going into the board. My fingers are curling into the paper. So, for part B, the magnetic field coming from the circle is just going to be this right here. So, B just equal and like I said when we started part B, is this problem is simply asking you to find the magnetic field coming from these 3 parts. 1, 2, and 3, and we know what 1 and 3 is. 1 and 3 is just going to be the magnetic field that we saw for part A, which is just going to be this. And remember that this is also into the board also. That means we can just write it as B is then equal to 2 times mu naught I. Just copy this again. 4 pi times 1 over this r right here, 1 over r squared times L over L squared plus r squared. And it's times 2 because we have both of these wires right here contributing to the magnetic field at this point. So 1 and 2, so times 2. Plus the magnetic field coming from the circle, which is this right here. Mu naught over 4 pi times I over r times pi, and into the board. And that's our answer for part 2. Because B total, you can simplify this if you want to. This cancels out and this cancels out. That's it. So I just wanted to talk a little bit more about finding the direction of the magnetic field. When we were doing a problem, the method that I showed in the video was I used my right hand rule and I knew that magnetic field goes around. So I was able to see that using right hand rule that magnetic field was actually going into the paper. But another good way of finding the direction of the magnetic field is also just looking at this cross product right here, which is IDL cross of R. And like I said in the video, DL, just think of it as a very small length, which is right here, a very small length vector. And you cross it with R, and you're able to get the same result. So the way you want to do that is you point your fingers in the direction of DL, which is going this way, and then you make sure your palm is facing the R vector, and then you curl towards R, and you're able to see that it's going into the paper. So that's another way of thinking about finding the direction of the magnetic field.